So before we start, just wanted to get a feel of participants. How many of you are, let's say, first year, second year, or third year PhD students who are pursuing research? Okay, very good. How many of you are attending this kind of talk first time? Cement chemistry related. Okay, good. So this talk will focus on supplementary cementitious materials. Okay, I think most of you must have heard of supplementary cementitious materials. Let me just hear from you. Why do we have to care about supplementary cementitious materials? What comes to your mind? Why do we have to use SCMs? Okay, once CO2, someone else? Durability? Take care of? Free lime, okay. Okay. Okay, all this is okay. Anything else it does to, cement hydration or phase assemblage? Okay, good. So there are a lot of things, right? Lot of things. We will talk about good guy from the previous presentation. What is that good guy? I meant to say good phase or important phase. CSH, okay? And so-called bad guy, what Professor Shashank was saying in some books, it was written, it's a bad guy. So we'll talk about these two phases and how SCMs alter these phases, okay? So when we talk about SCMs, obviously prominent ones are slag, fly ash, silica fume, metakaolin, you must have heard. Calcine clay, which has been also now quite popular, a lot of research has been done. But you see in this ternary diagram, you have a lot of other SCMs, potential SCMs, like natural pozzolan, right? And you have non-ferrous metallic slags, ceramic waste, biomass ash. And this ternary diagram shows like where these SCMs fall, right? And what we mean by this ternary phase diagram, one apex you have silica, one apex you have combined alumina and ferrite phase, and one you have alkali metals and alkali earth metals. If you combine all, in one, so you see the kind of distribution. So we have a range of these SCMs, right? Depending on source. So before, using these SCMs, we have to look at a lot of things. We cannot, like if I give you a powder, hey, SCM, can you use it in concrete? First, you must assess the SCM. You should look into its properties, physicochemical properties, and its reactivity. That will help you better use the SCM, that specific SCM in concrete. So in this lecture, we'll look into basically the aspects which are very, very important before we use these SCMs, okay? And we'll also look into the impact of conventional SCMs on hydration, phase assemblies, things like that. So what is the outline of this presentation? We'll look into the influence of SCMs on CSH characteristics, so-called, how it alters calcium silicate hydrate, which is the prominent phase in cement hydration. And we'll look into Feeler effect, which is also very, very important to understand when we look at the effect of SCMs on hydration kinetics, how it alters the phase assemblage, how it alters the pore solution chemistry. That also plays a big, big role when we evaluate these SCMs. And at the end, any material we use, reactivity becomes very, very important. We would like to know how reactive this material is. Is it reactive? Is it inert? So what are the ways we can evaluate these SCMs? So basically, my presentation will touch upon all these aspects. By the end of the talk, you will hopefully have understanding of all these aspects, and you'll be ready to evaluate any SCM which is there in your region, because it depends on region. You may have different types of SCMs. Okay. So let's look at this ternary diagram and look at the different hydrated phases. Where will they be on this ternary phase diagram, right? So this is again a CSA ternary phase diagram, and you see calcium silicate hydrate. Now that 1.7, right, what Professor Shashank was referring to, kind of an average figure for the calcium to silicon ratio of CSH, which is formed in hydrated Portland cement. Okay, it averages at around 1.7. But see, if you go towards this silica apex, that your calcium to silicon ratio will reduce. So you have, let's say, 0.83 on this. Then you have a lot of phases on this line, right, connecting CaO and Al2O3, right? AFT, which has more calcium. Then you have AFM, or AFT will have, like AFM will have more alumina. So you see, as you move from calcium, this corner to that corner, how the phases are changing, right? Now, if you have phases like calcium aluminosilicate hydrate, let's say CSH incorporating alumina, you are somewhere here, right? Then some phases like stratlingite can also be found here. So depending on, again, chemistry, you will have different types of phases, and also thermodynamics will govern what kind of phases will form, right? If you have only calcium oxide and alumina, you are never going to form CSH. You will always be on this line, right? If you have only calcium oxide and silica, you will not have alumina bearing phases. So we are not going in detail in that. Hopefully in thermodynamic modeling lecture, you will get gist of that. Essentially, cement hydration is dissolution precipitation reaction. If you have to understand cement hydration, things are dissolving, and then new things are, reaction products are precipitating. So it's a dissolution precipitation reaction. Dissolution is governed by undersaturation. Precipitation is governed by supersaturation, right? Simple example is, if you start adding salt to water, initially you won't see it, but if you reach that limit, it becomes supersaturated, you see deposition of salts, right? So, as we understand, if you look at the Portland cement and hydration of Portland cement, the CSH present in hydrated Portland cement, roughly C to S ratio will vary from 1.5 to 1.9, averaging at 1.7. It's not fixed. But what happens when you add silica-rich SCMs? So it changes the C to S ratio. It lowers the C to S ratio. Now the CSH, which is formed, will have lower calcium to silicon ratio. That's very, very important, that kind of change, right? So it's changing the chemistry. And this structure is similar to basically the tobermorite-like structure with many defects, right? So again, I think with the later talks by I think Professor Keshav and Professor Aslam will touch upon this little bit. So we are not going into that detail just for now. It has a tobermorite-like structure with the defects. And also there is a change in the chain length. Okay, how long is the chain of the CSH? These are sheets, right? If you remember Feldman's Sharada model, you have sheets. Now these sheets, whether the length of these sheets is changing, right? Mean chain length we call. So depending on type of CaSH, calcium aluminosilicate hydrate, whether it is cross-linked or non-cross-linked. I am just showing you both. This is a cross-linked one, right? So these sheets, these are calcium oxide layers, and on this you have a silica tetrahedron, right? This is another calcium oxide layer, and you have a silica tetrahedron. So it could be cross-linked, and in this case you have a non-cross-linked. And between these layers you have ions, like alkali ions, you can have water molecule, right, present between these layers. That's what we call, interlayer water. So you can use, we can calculate the mean chain length, right, MCL for non-cross-linked CSH. We can then evaluate the alumina to silica Al to Si ratio. I'm not going in detail. Again, this detail, you can do NMR. From NMR, we can get Q1, Q2, Q3, Q4. These are different coordination, let's say, of your tetrahedra species. So we can get an idea about how the chain length is, how this length is changing when we add SCMs. Okay. So typically what we see here, you see this is 100% Portland cement. And as we add metakaolin, right, that's just an example, right, reactive aluminosilicate material, your chain length is increasing, right? It goes up from 2.62 to 7.24, right? And you see here again this chain length, right? This one is example of, you have chain length of 5. This is a pentamer, right? So 1, 2, 3, 4, 5, right? Here you have octamer, right? So if you count, and this, the blue one is basically alumina, right? So this always is in the bridging position, not the paired position. And based on this, if we know this, we can calculate what will be the AL to SI ratio, right? 1 divided by 7, 1 divided by 7, in this case, 1 divided by 9, right? This is the defect for an example. So these are some of the ways we can kind of calculate the mean chain length, we can calculate calcium to silicon ratio, we can calculate alumina to silica ratio. Why is it important? That will tell us how much incorporation is there, right, in CSH. And we'll see the implication. Now we understand that the calcium to silicon ratio is going to decrease when we use these SCMs. So what happens? First, it's pretty clear that if we are incorporating alumina in CSH structure, that changes the basal spacing, okay? The interlayer, I mean the distance between these layers. So you clearly see as the C to S ratio is decreasing. Let's say this is one, this is conventional one, right? As this is decreasing, your basal spacing is increasing, right? So it happens in both, right? If you look at CASH, CSH, you see kind of makes sense, right? Something is getting incorporated, it's affecting the interlayer basal spacing. But it can only incorporate to a certain level, right? So if you keep adding, again, up to, let's say in this case, 0.1 AL to SI ratio, it was fine. But beyond that, if you add more, then it will precipitate. That extra alumina will precipitate either in form of stratylingite or K2-ite phase. That's what it says. So CSH can only uptake to a certain extent. Beyond that, then you have alumina bearing phases which will get precipitated. Now, what is, so this is interesting. Now, very important, I think it will have implication on ASR also. What happens when your calcium to silicon ratio is reduced, the alkali uptake, alkali binding increases. Same CSH will be able to bind more alkalis. Okay, and this is the result, very interesting study done by Hopdal. I don't know if I'm pronouncing it correctly. Shashank can correct me later. So C to S ratio, right? Say if you look at the C to S ratio of CSH, right? If it is at 0.8, for an example, the alkali to silica in the total solid is significantly higher than this case, right? It's pretty obvious that as C to S ratio is reduced, alkali to silica ratio increases. So it can bind more alkalis. And I said it has implication on durability. For an example, alkali silica reaction. Let's say in cases where you have reactive aggregates, right? Reactive aggregates. So now you have a pore solution which has high pH, and these aggregates will have tendency to react, form alkali silica gel. Now, if you can somehow reduce the alkalinity of pore solution, right? So alkalis now are not freely available in pore solution. They are bound by CSS, calcium aluminosilicate hydrate. So that also reduces the susceptibility towards ASR. Anyway, we are not going to talk about that, but this has a consequence. So these are some of the changes you see in the structure of CSH. It's a binding capacity when you introduce SCMs. Another example showing you here, again, increased alkali uptake at lower calcium. So it's pretty well understood. Okay, how the alkali binding changes as C to S ratio is reduced with the introduction of SCMs. Okay, now so we are going to talk about so-called bad guy. May not be bad because it buffers the solution and provides passive layer on reinforcement, which is very good to improve the corrosion resistance. This calcium hydroxide, right? So what is pozzolanic reaction? When this calcium hydroxide reacts with basically reactive silica or alumina to form additional CSH or calcium aluminosilicate hydrate, right? So this is a very interesting reaction. It is lime consuming. We are consuming hydrated lime, right? It refines the pore structure. It refines the interface, right? But it's slow. Slow means low heat of hydration. It's not very fast. It takes some time. And also it gets affected by the alkalis and gypsum. Now if you look at this schematic carefully, what you see, not just SCMs, right? If you introduce like a ternary system, when you have limestones, which is a case in LC3, you have some additional reactions in addition to pozzolanic reaction, right? So you have formation of hemicarbonate, monocarbonate phases, which stabilizes your Eternite. The AFT to AFM conversion doesn't happen. Anyway, we'll discuss briefly about this. I hope this has been covered in LC3. I will just touch upon that. So these are some interesting, synergistic effects which take place when you have, let's say, limestone in addition to SCMs. You see refinement of the pore, and overall improvement in the durability. So as I said, pore solution composition changes drastically, and obviously it will depend on type of SCM, whether it is fly ash, slag, silica fume, metakaolin, calcine clay. Typically, when we blend PC Portland cement with silica fume or low calcium fly ash, it will lower the alkali content, and hydroxyl, like pH, will reduce. If you measure the pH, let's say if you are able to extract the pore solution and then measure the pH, you will see the reduction in the pH. But in case you have if you have a SCM which has high alkali content, then you may not see that much drop, right, initially. And so this we know, and so this is fine. This is with respect to CSH. Now another thing is filler effect. All of you must have heard of this filler effect. Basically, if you look at, so there was a study, very landmark study, 1990 by Gutierrez and Delgiel. What they showed is, if you just add rutile, what is rutile? Titanium oxide, inert material, right? So you see this is with rutile and this is without rutile. You see the difference, right? What they notice is, if you add a non-reactive material, non-reactive, and if you look at the degree of hydration, you see enhancement. Okay, so this was called kind of filler effect. Something is happening, you are adding. Obviously, there will be more effects when you have a material which is also reactive. That's the case with the kind of materials we use. So what could be the reason for this? There are a lot of effects which take place. I mean, a lot of the changes are there, all right? You provide increased surface area, you have more water, right? More water for per unit mass of cement particle when you use these fillers. So overall, these things result in improvement in the heat of hydration, right? And you can see similar effect here also when this silica fume is added, right, to PC, how it increase the heat of hydration. So what could be a way? So there was an interesting study done some time back where they looked at this area multiplier. So that could be one way to kind of quantify the filler effect. If we want to quantify the filler effect, let's say, limestone, for an example, of different sizes, ranging from 0.7 micron to 40 micron. Can we compare these, right? So again, this filler effect, they came up with this area multiplier, right, which is proportional to the specific surface area of filler, and it's a replacement label. You can come up with this area multiplier, and perhaps that can be used to compare different types of, it's the same material, limestone, of different sizes. What will that change? It will change the specific surface area. Okay, that's the number which is going to change. So it tells us, right, 0.7 size has higher area multiplier, and how that will affect the heat of hydration. And this was again used for quads, right? Quads of different sizes. And this could be one way to quantify. When we talk about a flare effect, how do you quantify? How do you compare different sizes? This could be perhaps a good way to do that. Now, what happens when you use limestone? Will the effect be same instead of quartz, which is inert? We see definitely difference, right? So you have additional, basically what happens is, when you have limestone, you have synergistic some reactions. Basically, it's more energetically favorable. Limestone surface is more energetically favorable substrate for CSH, which you don't have in the case of quartz. So you have some additional benefits when you use limestone, right? So you see here, what we are looking at is the heat flow, right? This is controlled, and what happens when you use quartz versus what you use limestone. So you have some additional benefits of using limestone. But this is because of just limestone, right? It's interesting. In this study, what they looked at is even with the quartz, let's say if you are using quartz, now if you add extra carbonates, right, extra carbonates, you can boost up, you can increase the heat flow. So basically what it comes down to is the limestone partially dissociates to your calcium and carbonate ions in solution, may later react chemically with CSH by annexes. So it has some additional benefits. The chemistry is such that there are some differences compared to non-inert material. As far as the phase assemblies is concerned, again, this is again the predictions based on GEMS. Again, there will be a lecture on GEMS so that you will use how this can be used to predict the phase assemblies. So what we see here, as the fly ash fraction increased, so you see the CSS structure, like composition also changes, right? Now we have more tobermorite or tobermorite like in a sense CSH with lower calcium to silicon ratio. Initially you have calcium to silicon ratio, high calcium to silicon ratio, that transitions into lower calcium to silicon ratio. Also there is a consumption of portlandite, as that will again depend on the amount of fly ash, right? And if you have significant amount of fly ash because of the reduction in the pH and all that, you are also monocarbonate destabilizes, you have formation of stratlingites, things like that. So this is again predictions, but it helps understand what kind of changes may occur in the system when we use just fly ash. So that was with respect to phase assemblies, and this was again a very extensive study. They looked at the pore solution. Let's say if you can extract the pore solution of the mixes with the fly ash, again it may be very difficult to see, but I'm just showing you prominent alkali metals like potassium and sodium, and how the the concentration changes with time, right? So one thing to note is only at higher replacement levels, right? Let's say 20, 30%, 40%, you start seeing a drop, right? What is it because of? It's again because of the alkali binding of CSH, right? Similar thing you can see here, maybe because there are a lot of data points you are not able to see it clearly, but this is well established, and this can be easily monitored. You can either measure the pH, you can also extract the pore solution and determine the concentration of potassium, sodium in the solution, and that will tell you how this pore solution composition is changing. Now silica fume is more reactive, obviously, more reactive material. We'll come back to the reactivity assessment later, but typically it has very high surface area, specific surface area, right? Very fine material. It's supposed to have very high reactivity. Similar kind of you see here, right? But compared to fly ash at smaller percentage, you can see a transition, right, to low calcium to silicon ratio CSH. And it consumes the portlandite also very fast, right? So you see here, initially you have some portlandite, but it gets consumed, right? So you have this, these, and obviously as this happens, if you add more silica fume, it will also alter the pH. Then pH reduction also destabilizes your eternite or phases like monocarbonate, carboaluminate. Okay, so those kind of changes are also evident in this. And this drop you see more. It's quite noticeable, right, in case of silica fume, because it reacts very fast, the changes are very fast. You see a drastic reduction in the potassium. Again, it shows you that the reduction in the alkalinity of the pore solution when you add silica fume. There are, you can see the hydroxyl, basically it will match the trend you see in case of like potassium or sodium potassium ions, sodium ions, you will also see in hydroxyl ions, right? So pH also drops here. So that's fine. Let's look at slag now. Slag is interesting. It brings a little bit more, like it has some calcium in it, right? So the kind of changes you have seen in case of fly ash and slag will be, here also eventually you will see, you will form, low calcium to silicon ratio CSH, but it will take some time. You need more slag for that, right? So you have high calcium to silicon ratio CSH, low calcium to calcium ratio CSH. It takes longer time, you need more slag to fully consume, let's say portlandite, but you have additional phase like hydrotelsite. Again, because of the magnesium, aluminum, it brings So you have this kind of phase. So chemistry, little bit phase assemblage changes when you have slag in the system. You may have Stratling-Guide kind of phase also. So depending on type of SCMs, we see changes in the phase assemblage and pore solution chemistry here also, right? You see that the drop only at higher, when you have higher replacements, let's say here, you see a drop at later ages. Okay. So limestone is interesting material. We'll see its synergy with calcined clay later. But first, if you just use limestone in US, for an example, PLC is very popular. Like in India, we use PCC, PPC. So in US, PLC, Portland Limestone Cement. So just adding limestone can also bring about a lot of changes, right? So you see here phases like hemicarbonate or hemicarboaluminate, monocarbonate kind of phases, which can be detected using X-ray diffraction. Again, if you are familiar with X-ray diffraction, it can help you detect these phases. And the chemistry also changes. So you see here, with the addition of 4% calcium carbonate, how the phase assembly changes. So you have formation of monocarbonate. Okay, in this case, in addition to eternite. So this is what happens, and we can also experimentally verify, like what kind of changes are brought in with the addition of limestone. But one interesting aspect which has again implication on system, when you have calcined clay, for an example, you have the role of carbonate ions, right? It stabilizes AFT. So what happens in conventional Portland cement system? You form AFT phase, and that once gypsum is depleted, it converts into AFM phase. So if you examine your hydrated Portland cement at later stages, you will find monosulfate. So there is a transition from AFT to AFM, and we know that that phase is also responsible for sulfate attack, external sulfate attack. For an example, if you have sulfates coming from outside, that AFM can react with additional sulfates and form AFT. That is a reaction which gives rise to or increases the volume, expensive reaction. So a lot of issues. But here, what we are saying that AFT is stabilized. So you see what it does, you form initially the carbonate, hemicarbonate, and later on, if you have more carbonates in the system, then you will form monocarbonate. Monocarbonate is also okay. You can say monocarboaluminate is more precise in a sense. So you form monocarbonate. But what it does is it stabilizes the AFT. So here you don't see a conversion of AFT to AFM. So that's also very interesting what these carbonate ions do with respect to the phase assemblies. Now, there was a discussion about the gypsum. How do you determine how much gypsum to be added, and why is it important? Because it's very, very important to have optimum sulfates, right? Traditionally, people used to optimize the strength, right? So you add 0.5%, 1%, 1.5% gypsum to your clinker and see which gives you the maximum strength and optimize your strength. But there are more scientifically accurate methods. One is calorimetry, where you just you make sure that your alumina is not overshadowing the silicate. Basic silicate aluminate should hydrate at after the silicates, right? So the peak should come after the main silicate peak. So what you see here, now if you look at these, there are 4 curves here, right? So this is OPC, the blue one. Now if you replace OPC with class F fly ash, you see this dilution effect, right? Because we are using only 70% of OPC, 30% fly ash is being used. Now, depending on type of fly ash, this was class F fly ash, in this case class C fly ash, it also accelerated. It reduced the induction period, right? That could be because of the calcium content, could be because of other regions also. And the LCD, for an example, you see here, right? So you see this needs to be balanced. So now what happens when we add extra gypsum, additional gypsum, right? You see the shifting of this peak. So that will ensure that this is not basically interfering with the silicate hydration. Silicate hydration is very, very important, right? So it should come after that. So beyond a certain percentage, then we know that, okay, now it's fine. So this could be one way to also optimize the sulfates in the systems where you have more alumina, from SCMs, which would be the case when you have fly ash, calcined clay, or metakaolin. Another example showing you the basically how gypsum addition can be used and what is its impact on the strength, right? So we can also look at the impact on the strength. Basically, criteria. How do you criteria? What is the criteria to use? Basically, eliminate peak occurring after silicate peak, and also eliminate peak not delayed beyond 24 hours. Otherwise, we'll have reduced one-day strength. So this is some of the things we can keep in mind. Yeah, so this was again shown by Professor Shashank. Change. Now, what happens when you have limestone and SCM, right? When you have a SCM with limestone in this, so traditionally you will have conversion of, eternite will convert into AFM. So you'll have monosulfate forming at the cost of, because that's what happens. So now in this case, you don't have this, you form additional like hemicarbonate and monocarbonate phases, okay? Obviously, because of the reaction, this calcium hydroxide content will decrease because pozzolanic reaction is still occurring, right? Pozzolanic calcium hydroxide will react with your reactive silica alumina, form CSH. So what will happen? CSH will increase. So these kind of changes happen when you have both SCMs and overall stabilization of eternite, right? That's important. Increase in the carboaluminate phases, lowering of Portlandite, increase CS. So overall, this improves the durability of the system. This is a slide borrowed from Professor Shashank. Shows kind of a synergistic effect in LC3, right? When you have calcine clay, limestone, you have these aluminocarbonate reaction. You have also pozzolanic reaction. You have filler effects. All physical and chemical effects are present in the system, right? Not just filler effect, but also these chemical effects. And overall, it leads to denser microstructure, leads to better, higher strength and durability. Okay, so now if we now dig deeper into SCMs, right? Eventually would like to understand how reactive these SCMs are. Obviously, composition of SCM will matter, right? Will determine its reaction rate. And we know that SCMs have a varied composition, as I showed in the ternary phase diagram, right? It can have alkalis, it can have more silica, it can have less, iron, more iron, depending on the source. The amorphous phase itself may change, composition may change, and we know that, it's amorphous phase which will govern the reactivity of particular SCM, or glassy phase. And it's a replacement level, right? Depending on the degree of, replacement level, we will have different extent of impact. pH also changes, right? pH also changes, or pH also will affect. pH will also affect the reactivity. Let's say SCM in a higher pH environment will react more, for an example, compared to an environment of lower pH. And temperature, right? Temperature also will impact the reaction kinetics. So these are some of the important factors which will influence the reaction rate of SCMs. So that's why it becomes important to evaluate the reactivity of SCMs. So this is kind of a last section. It's very, very important. A lot of research is being done in this area. If you are looking into the reactivity of SCMs, a lot of state-of-the-art reports have been published, like from Rylam, prominent researchers like Ruben Snellings at IIT Delhi, IIT Madras, Pranoy Suraneni at University of Miami. They have extensively worked on this. So, so let's look into this. How do you want to evaluate the reactivity of SCMs? Let's look at first the glassy phase, right? Amorphous content. Basically, any material will comprise of two phases, like amorphous and crystalline. So basically, if you really want to understand the reactivity, we need to dig deeper. What is its amorphous content? Let's say what kind of amorphous content phase is there in the glass versus what kind of amorphous phase is there in your fly ash, slag, or could be any other material, right? So this is an interesting study. Those of you who are interested can again go through this work done 10 years back. They looked at the model glass. So because of the variability we see in these materials, first thing is to synthesize these model systems of different compositions, right? So what you see here, in this study, they looked at kind of a system, synthetic system, which has these components, right? And we can vary. We can vary these vary the composition. For example, this silicate, it was primarily silicate, then you had calcium silicate. Let's say you have some more calcium, right? Then you have aluminosilicate, right? Now you can see you have more like calcium-rich aluminosilicate. So basically, calcium-rich aluminosilicate could be like a slag phase, right? Slag will be similar to this. If you have aluminosilicate, it could be, let's say, calcine clay, right? Silicate, just silicate could be silica fume, right? So these are the model system where you exactly know the chemistry, composition, right? So these can be synthesized. You can synthesize these. Now, when we talk about the glassy phase, we have to ensure that these are cooled at very, very fast rate, right? If we cool these slowly again, you will form the crystalline phases. So that's what we do when we make clinker also. The cooling is very, very important. You ensure that so that you don't give time. If you give in a time microstructure, it will eventually form crystalline phases. That's the stable phase assemblies. But if you cool it very, very fast, then you will form amorphous phases. So that's what is done. So typically what we can do, you see in this X-ray diffraction, you can see the typically hump depicts the amorphous nature of a material, right? So you see amorphous hump. So that shows that this material, whatever synthetic material we are talking about, has amorphous content. But also you notice there is a difference in amorphous nature. All are different, right? So here you see hump between 20 to 30. In this case, you have it shifted towards the right. So it shows you that when we talk about the amorphous phase, it changes depending on the composition, right? And again, if you want to show it on this ternary phase diagram, you can see, right, where it would be, right? So we are interested in whether all these different types of glasses react similarly or there is a difference. That's the thing, right? We would like to know the difference in the reactivity. So what they did, they dissolved the glass, right? So reactivity, simple, we want to look at how fast glass is dissolving, right? So we can track the silicon concentration, Si concentration. And with time, if you want to plot, okay, we see some differences, right? We see this blue ones, which is like a D, right? Which is a calcium-rich aluminosilicate is here compared to other glasses. So that's quite noticeable. And also you can calculate you can look at the silicon present in the undissolved material. There are ways to determine that. Obviously, it will be just opposite. Makes sense, right? So it dissolved more, so it will have less kind of thing. So so what drives this reactivity? In this case, you can see you have these network modifiers. You have bridging oxygen, non-bridging oxygen. Let's say in this case, you have this bridging oxygen, right? And here you have this non-bridging oxygen. So imagine that if you have more non-bridging oxygen, then you have these defects in the system. If you have more defects in the system, then it's more reactive. So somehow if you can, let's say, if you can estimate the fraction of these non-bridging oxygen, right, in your system, should be able to tell you roughly, reasonably well, the difference in the reactivity. So that's what these guys did. And you can see if you calculate this NBO over T, corresponds to more, non-bridging. Basically, if the number increases, that means the glass is more depolymerized, right? And that basically is, the reactivity also is directly kind of, you can see a trend. As this NBO to T is increasing, your reactivity index also increases. That could be one way to look at different types of amorphous phases, which may be present in your SCM, right? So, so basically we can look at we can break it down to the reactivity of the glassy phase, right? We can look at the extent of depolymerization because that will affect the reactivity. And the maximum dissolution rate is related to the chemical composition, but actually rate will depend on your conditions like solution condition, pH, temperature, things like that. Now let's look at some of the reactivity tests. A lot of work is being done these days to evaluate these SCMs, right? Because we cannot just put anything. We need to ensure that they are reactive. And different types of tests have been proposed, right? This R3, modified R3, and what it says. Basically, essentially, you are mixing, let's say in R3, SCM with calcium hydroxide in presence of calcium hydroxide, sulfates and carbonates. That's the environment you simulate. And then you cure it for a certain time, you monitor the heat release and bound water, right? And then examine its reactivity. Modified R3 slightly changes, the temperature is increased. It's specifically for the slowly reactive SCMs. Okay, then you have lime strength test. You add simply lime, right, calcium hydroxide, right, and that you look at the strength of mortars. Then like bulk resistivity index test is also there. So I will just show you some of the interesting results. So this was again done using MR3, modified R3. It can help you differentiate different types of SCMs. So what you see on the y-x-axis is calcium hydroxide consumption, right? Again, why we are talking about calcium hydroxide consumption? Because pozzolanic reaction, right? So if there is a significant consumption of calcium hydroxide, that mean that it's a reactive, right? So reactive system. And on the y-axis, you have a heat release. Also, that tells you about the hydration. So inert somewhere will be here, very low consumption, low heat. And then you have some pozzolanic, less reactive system. You have pozzolanic, more reactive. These boundaries are not well defined. Again, this was proposed in this study, but you see kind of a scatter, right? Differences. You can see what kind of, there are some latent hydraulic system, but more reactive, right? So this was and typically what they say, I mean, typically if the heat of hydration is less than 120 joule per gram per SCM, then it's considered inert. More than that, depending on what is the range, let's say 120 to 360, it's less reactive, more than 360 joule per gram of SCM, and all this can be easily done using isothermal calorimetry. And this was the study done by Neela, where we looked at the different types of biomass ashes. And if you follow, let's say in India, we have a lot of biomass ashes, right? Depending again the source, whether it is rice husk or sugarcane bagasse, whether it is mixed with the petroleum coke, your composition will change. It may have alumina. So again, this can be classified, right, into whether it pozzolanic less reactive, pozzolanic more reactive. Finally, modified lime reactivity test. Again, sometimes it becomes difficult to demold the samples because of the slow strength development. So what we change is we slightly change the temperature so that, the limitation is addressed by MLRT by alkali activation. When you add little bit more alkalis, so basically even the the SCMs which are not that reactive will react little bit at faster rate, and with the elevated temperature also we enhance the reaction kinetics. So that's the change, and that also is one way to evaluate the SCM. Again, the type of test we use will depend, right? Let's say first you have to see conventional tests. If you are not able to see the difference, then perhaps you'll have to go for modified tests. So SCMs basically improve the microstructure of concrete, by refining the pore structure, and it alters the basically CSH structure, its binding characteristics. So that way it reduces the pH of the pore solution, has implication on ASR. And depending on the type of SCMs you use, let's say limestone in combination with SCM, you may have synergistic effect where you have stabilization of eternite AFT phase and formation of some additional like hemicarboaluminate or monocarboaluminate type of phases. So that way each SCM will behave differently, but these are some of the major things we need to keep in mind when we look at the SCM. So with that, I will conclude my talk. And some of the references, if you would like to, get deeper into this topic, and still a lot of work is being done. I think, please, a lot of researchers these days are looking into the reactivity of SCMs. So it's a good area from research perspective also. Thank you.